Faraday's law of induction says that there is an electromotive force represented by curly E, which comes from taking a number of loops of wire and having a change in magnetic flux happen over a period of time through all of those loops. That creates an induced electromagnetic force, in other words, a voltage, which is being caused by this change in magnetic flux through all of those coils of wire. Magnetic flux, delta phi, has to change in time through the number of coils of wire, capital N. Of course, if you have only one coil of wire, N is equal to 1. And we make an assumption here that all of the coils have the same area, so all we have to do is count them up rather than treat them individually as individual areas. Also, don't forget that if I've got a delta over a delta formula, we can make those deltas small enough to become differentials, and then that turns into a derivative formula. So this would also work if you actually know your phi, your flux, as a function of time. Then you could take the derivative of that function of time, multiply by the number of coils to figure out your electromotive force, or how much voltage you have going through those coils of wire. If there's an electromotive force, then remember that's a voltage, and therefore there's going to be a current through those wires. If somebody can tell you the resistance of those wires, and you can use Faraday's law to figure out the voltage, then you should be able to calculate using Ohm's law how much current you have going through the resistance of those coils of wire. And then there's going to be another question that's going to come up. What is the direction that the current is going? Now, the minus sign that we see up here in Faraday's law of induction is supposed to help give us a clue as to what is the direction of the current in these loops. But what we're going to find is it's going to be easier to use Lenz's law to figure out the direction of the current.